Hello, everyone, and welcome to today's webinar, A Different Approach Towards Limit State Design of Geosynthetic Reinforced Soil Structures, brought to you by the International Geosynthetic Society's North American Chapter and the Geosynthetic Materials Association. My name is John Allen, and I'm a Vice President for IGS North America and a Geosynthetic Materials Association member, and I will be your moderator today. IGS North America has teamed with GMA to provide these free educational webinars. You should know that the International Geosynthetic Society's mission is to educate the industry about geosynthetics. We do this in several different ways. One example is this webinar that you're attending today. We also provide educational classes to civil engineering professors so that they can introduce geosynthetics into the engineering curriculum at their respective universities. And we help coordinate and host industry conferences. GMA provides engineering support, business development opportunities, educational programming, government relations, expertise, and industry recognition. GMA also influences specifications and lobbies on behalf of member companies and targets key US states to expand the geosynthetics market. GMA also provides a network to exchange information, solve common problems, and develop mutually beneficial relationships. Before we get started today, I'd like to go over a few items so you know how to participate in today's event. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions box of the control panel. You may send in your questions at any time during the presentation. We'll collect these and address them during the question and answer session at the end of today's presentation. The recording of this webinar and PowerPoint will be made available after today's presentation if you wish to go back and refer to it at a future time. I would now like to introduce our presenter, Dr. Ben Lashinsky. He is an associate professor in geotechnical engineering at Oregon State University. Dr. Lashinsky's primary research interests focus on slope stability, reinforced soil, and the application of geomechanics towards assessment of natural hazards. Please welcome Ben.
Well, thank you very much, Sean, and thank you all for being here today. So today we'll be talking about limit state design for geosynthetic reinforced structures. And I have to admit that this is not just my work, but the work of several Lashinskys listed here. Just a quick note, as John mentioned, if you have any questions, feel free to send them along, or feel free to contact me at any time after this presentation. I'd be glad to clarify anything. So thank you all for being here, and we'll get started. Let's start with the roadmap of the presentation today. Let's first talk about why is a limit state analysis needed, and then we'll talk about some of the methods that we can use for strength limit state analysis. We're going to focus mostly on limit equilibrium, talk about its kind of global application, and then kind of move into some of the technical details associated with this, including the safety map, the baseline solution, which is the kind of the new material we're presenting today, how we apply the baseline solution to design of geosynthetic structures, and then a bunch of illustrative examples to maybe kind of cement the concepts we've discussed today. Finally, we'll have some concluding remarks and definitely some time for questions. So let's get started. Why do we need a limit state analysis? So let's talk about the strength limit state. That strength limit state is one piece of design of geosynthetic reinforced soil structures, and basically it represents the point where the full capacity of the soil shear strength and the reinforcements too is mobilized. So it's on the cusp of failure. A butterfly lands on this structure and it collapses. So failure at the limit state is a realistic possibility if design's poor. Often there's issues with design that relate to construction, poor drainage. We've all seen pictures of failed MSE walls, and we know that limit state failures do happen. The way we avoid these catastrophic failures is basically by assigning an adequate margin of safety in design. As engineers, we like to be conservative. You know, safety is one of our priorities. So we often design these structures and have some kind of safety factor assigned to either the reinforcements or the soil or both, and we'll discuss some of that today. To quantify what that margin of safety actually is, one needs to reliably predict these limit state conditions. So in theory, design, considering, say, serviceability, the displacements and deformations of a wall, if done correctly, should eliminate any possibility for that limit state strength failure. However, as we all know, predicting displacements in practice is not a common thing to do, and we're not really able to do it that reliably. However, predicting failure or a strength limit state is pretty reliable and based on statics that have been around for quite a while. So common practice happens to be that design for the limit state assumes that if we have an adequate margin of safety, we can safeguard against any failure, and maybe by virtue of having the conservatism implicit in this, maybe it will satisfy serviceability too. Here's a picture of a failed MSE wall in Alabama. You might notice it's right next to a fireworks stand, and thankfully the failure didn't go all the way in there, or otherwise this might have been a more interesting presentation. But what we see is kind of your typical failure in an MSE wall. Failure occurred in the upper wall section, usually implying that water probably played a role. And in this case, it's a connection failure up in the upper portion of the wall where, say you have the right amount of blocks or the right block facing system or connections are adequate. You kind of wouldn't expect a failure there under the small earth pressures that are typically realized. Typically, we expect the largest earth pressures to be at the base of the wall, and if anybody's done a slope stability analysis, that tends to be critical. So one might ask, how are connection loads evaluated? In current design, we often assume that those connection loads are equivalent to the maximum load we see in a reinforcement system. But in reality, they might not be, and they might be transient, dependent on some of these conditions like water. So let's talk about available methods for limit state design. So the premise of limit state analysis, as we discussed, is that failure is imminent. It's just about to happen. We're designing for the worst case. We're using all the soil strength. We're using all the reinforcement strength. This slope is going to collapse if anything happens. The premise of limit state design is that in its current form, we kind of look at developing an active wedge or some active body that's resisted by the reinforcements. Based on that kind of critical failure mass, what we can do is select a reinforcement with a long-term design strength, that's what LTDS stands for, with an adequate margin of safety against failure. Then what we can do is kind of verify the existence of this margin of safety on the strength of the soil, kind of producing working load conditions. So analysis is the basis for the design. It defines that imminent failure. It defines the critical case that we're trying to design for. It defines quantitatively what we need to apply a margin of safety to. Let's talk about what's out there. The conventional limit state design method that most people are probably familiar with is the one presented in Ashtel. And what it is, it's basically an earth pressure based approach. For the most part, it's semi-empirical. It's based somewhat on statics, but basically earth pressure theory. But it is somewhat empirical, accounting for, say, the extensibility or inextensibility of reinforcements, basically meant to represent working load conditions, not necessarily the strength limit state. The good news is that, well, it's safe, it's proven, it's done a good job for a lot of walls designed so far. And fortunately, even with these very conservative design criteria, it's fortunately economical and still a great innovative technology. And this approach is pretty easy to use. But whenever anything's easy to use, there's constraints, there's boundaries on when it's applicable. One of the big ones for this, and one that I've heard many people kind of complain about, is for this type of approach, the batter is limited to 20 degrees. So that means you can't have, if you have a slope greater than 70 degrees, it's a wall. If it's less than 70 degrees, it's a slope. And now, your engineer judgment, your intuition would tell you that physics probably doesn't change at this arbitrary threshold. Another restraint is that, okay, the earth pressure approach works great for simple structures, simple MSE wall. Anybody who's designed MSE walls realizes that simple is a lot less common than complex. Often when we're designing a structure, we're dealing with site conditions that are difficult. We're dealing with a right-of-way issue. We're dealing with water. And we might even be dealing with other complex things, surcharging, other loads. Most walls are complex. And earth pressure theory does not so easily shift to account for these complex conditions. So it's tough sometimes to extrapolate these earth pressure approaches to complex yet realistic geometries. And another thing we have to ask ourselves is it adequate for limit state conditions, strength limit state conditions? Conversely, Could it be overly conservative or even under-conservative? Let's take the opposite end of the spectrum for analysis. Let's talk about continuum mechanics very quickly, so nobody gets too bored here. But basically, finite elements, finite difference. What this is, these numerical models are useful for simulating working stress conditions, certainly. It's a pretty comprehensive approach, bounded in statics, in mechanics. And it's valid for walls and slopes. It doesn't look at that arbitrary threshold of, say, 70 degrees. It's valid for walls and slopes, but it's more complicated than AASHTO. It's not something you do in a spreadsheet. It can be useful in identifying potential failure geometries in complex problems. However, for anybody who's used finite elements or finite difference, it requires a little bit more input than just the friction angle or a cohesion or a unit weight. It also requires parameters that describe deformation, which sometimes aren't so easy to just pinpoint. So for those reasons, it's not a common design tool in the US. It's certainly being increasingly used for design. However, there's still a lot of uncertainty that surrounds some of those parameters that we don't have, that we have not pinpointed so well. Also, by virtue of capturing this critical mechanism, this critical failure mechanism, that's very useful. However, it doesn't give us kind of a holistic, broad view on the reinforcement tensions at the strength limit state conditions for a multitude of possible failure mechanisms. We capture one, but what about all the other possible failures? So let's talk about limit equilibrium, which is going to be the focus of today's webinar. So limit equilibrium is pretty simple to use. It's been applied to complex problems, and we have vast experience using it. It's been around for quite a long time, in fact, the 1700s, and for the most part, it's basically just basic statics. Reinforced soil is a subset of the slope stability analyses that limit equilibrium methods are commonly employed to, and limit equilibrium methods, or LE, can capture the effects of reinforcements at the strength limit state. Of course, there's definitely considerations and constraints, and one of the big ones is kind of the compatibility between dissimilar materials that needs to be considered. So a common consideration here might be the fact that, if we have to consider how extensible a reinforcement is versus the soil itself. So, for example, geosynthetic reinforcements might stretch enough to enable mobilization of the shear strength of soil. Steel or metallic reinforcements have different considerations. However, the current approach of LE is a bit half-baked. It's used in design, it's effective, it's proven, it does a good job, but we kind of have a mishmash, a pieced-together approach of limit equilibrium that's not necessarily efficient or as good as it can be. We're missing some useful information in our current approach. So the current way it's applied is that we often determine the strength of the reinforcement globally for a singular worst case. We look at a bunch of failure mechanisms, and we determine which singular failure mechanism gives us the maximum reinforcement load for stability. However, by searching just for this maximum, we lose a lot of useful information that relates to practical, everyday constraints in design, connections, and things like that. And that's overlooked. And we'll talk a little bit more about that today. So let's delve into limit equilibrium and how it works, just briefly. The oldest limit equilibrium approach was developed by Coulomb in 1776, a couple years ago. And basic approach was not considering reinforcements, but considering gravity walls and earth pressures, basically. The earth pressure resultant considering cases that aren't so simple. And what it is an active or a passive wedge, but in this case we'll focus on active. An active wedge forming for gravity walls. And the basic objective of the Coulomb approach, which you probably applied in undergrad or currently in practice, is to find that maximum active resultant force acting on your structure. The physics are timeless here. They still apply. It's still a great approach. And what we assume here is that in this force equilibrium approach is that a small outward movement of the wall enables the active wedge to mobilize its full shear strength. The soil is mobilizing its full friction or cohesion if you consider it. An active soil wedge forms, and eventually we drop from at-rest conditions to the active case. Now note, just because an active wedge forms does not mean that failure occurs. This is just kind of a technique to determine what that active resultant is so we can design a gravity structure correctly. But we're not here to talk about gravity structures. We're here to talk about reinforced slope stability. So Coleman's approach, 1800s, we're fast forwarding about 100 years. And what we have here is we're looking at the same kind of wedge. It's a forced equilibrium approach, just like Coulomb's approach. But we can apply that to look at Tmax. We can look at reinforcements by looking at the intersection of the wedge and finding the reinforcements that yield force equilibrium. So as opposed to a wall moving outwardly just a bit to enable active conditions, here we're looking at small extension of the reinforcements to form the active wedge. And what that does is it enables us to determine the load, T, required for stability. So just as before, note that formation of the slip surface, it doesn't mean failure. It just gives a condition where the reinforcement is designed to resist that active soil wedge. Now, let's get a little bit more complicated, but it's the approach we'll apply today. And just so you know what it is, we got to talk about it for a second. So the Coleman wedge is a force equilibrium approach, and it doesn't so readily account for a lot of realistic conditions like different soil types, layered soils, surcharges you can be accounted for, but not so easily. Here I'm applying Bishop. So this was developed in 1955, and it's a circular arc. It's a moment equilibrium approach, and it could easily be modified to find Tmax, or the max sum of Tmaxes throughout a failure surface, assuming that Tmax is the same throughout. It's a method of slices approach. It can account for layered soils and complex problems. And the beauty of these types of approaches when you're accounting for a circular arc is that, well, it can degenerate into a planar surface if you have a radius way out in space. It basically becomes planar. However, the Coleman approach, that can't turn into a circular surface, which might be critical in a lot of cases. And this approach, like those before, those limit equilibrium approaches, is valid for slopes and walls. No difference is made based on that 70-degree slope or that 20-degree batter. So there's some physics that goes into it, and basically the Bishop formulation looks at one surface or a series of surfaces discretized by a bunch of slices. And for each surface, we get a safety factor, and that represents the level of stability of that singular surface. The safety factor in the case of Bishop is defined as resisting moments versus driving moments. And by virtue of applying this for many surfaces, we can find a minimum safety factor, which we call the factor of safety. They just flip it around. So real quick, this slide's a bit dense, but bear with me. We'll see some figures coming up. Current limit equilibrium approaches basically determine the reinforcement strength, they determine the factor of safety, that is, or safety factor, of a surface that intersects a bunch of reinforcements. And we can determine whether our wall is designed well or a slope is designed well based on the reinforcement strength at each intersection point. However, once we do that, now we got to design for other things. We got to design for pull-out resistance, usually at the rear end of the reinforcements. And this is something that's not really implicit in our approach. It's kind of a second step we have to do. Let's talk about the actual available strength in a single reinforcement layer. Let's take a single reinforcement at the top of the wall. We have, say, a rupture strength of the reinforcement. Let's call it the long-term design strength, TLDDS. Now, to have that strength available, to have kind of a failure envelope here, we need to mobilize sufficient pull-out resistance, both at the front of the wall, at the connection, as well as at the end of the wall. It needs to be anchored sufficiently. So the maximum strength required to meet the design criteria of limit equilibrium has to first be determined. That's the way it's done currently. And then what we do is we check the anchoring and rear pull-out resistance. That dictates how long we have to make the reinforcements. If pull-out occurs, if we see it being critical, we have to lengthen reinforcements. And that changes construction specifications, excavation, all that. It costs money. So rear and front end pull-out resistance enables us to mobilize that long-term design strength. If we want to actually have the reinforcement mobilize its strength, it's got to have sufficient pull-out resistance both at the front and back of the reinforcements. So essentially, this green failure envelope dictates what's available in a given reinforcement. You can't get the full reinforcement strength at the back of the reinforcement because pull-out's critical, neither at the front. So while this is implicit in design, because we usually determine it in a secondary stage, it's not really considered for lots of different failure geometries, and we make some big simplifying assumptions regarding this. So that's dense, but let's make it a little bit lighter. We'll talk about the safety map, something that many of you are likely familiar with. So the safety map it's basically a diagnostic tool for slope stability. It was first determined in 2001, and now is readily available in a whole suite of commercial software. And basically what it is it takes one surface, two surfaces, 10,000 surfaces from Bishop or Spencer method or any slope stability analysis you like. And it shows them on your given slope geometry, providing a color-coded representation of safety factors, as well as the critical failure surface. So what that does is kind of lets you visualize swaths of instability or stability throughout a structure that aren't so readily determined when you look at just one critical surface. So basically that safety map is a diagnostic tool for looking at the current state of stability in a reinforced mass. And the design objective of using the safety map is to, applied to reinforced soil that is to select the strength and layout of reinforcements as to produce factors of safety that are at or above the minimum factor of safety required by design. So what that means is, you guess, you have a wall, you have a slope that's reinforced, you have a layout that's prescribed, you run your safety map, and you hope, given the strengths that you've selected, that your factor of safety is greater than, say, 1.3. And if it's not, up the reinforcement length, up the reinforcement strength, until it is. Now, that works, but it's not necessarily completely efficient. And we've thought of a way that might provide informative information more efficiently. So, while this meets design requirements, there's a lot of surfaces that are also over-designed. And I'll show you what I mean in a picture. Let's take a simple slope and talk about the safety map. Here's a slope here, and it's pretty simple, but it's got a broken back slope, it's got a toe slope, and you can see the dimensions as shown. It's a pretty steep slope, gamma of 127 PCF, a friction angle of 28 degrees, and no cohesion, because cohesion can really curse you. It's there one day and not there the next. So, just intuitively, I can tell since there's no cohesion here, and we just have friction, well, that slope is way steeper than 28 degrees. I don't feel too good about the design. You run a safety map, and here's what you get. This is a pretty simple monochromatic safety map. So 1.3 is commonly the design for stability for reinforced slopes or reinforced walls, and we see that there's a range from 0.27 to 1.3 for safety factors in red. There's a whole large area that's not stable in this slope here. The critical surface coincides with the face of the reinforced slope, as one might expect when you have no cohesion and you have a slope way steeper than your friction angle. It's basically the Coleman or infinite slope failure mechanism. In this case, the critical factor safety is 0.27. Now that's not very useful. All we know is that we have to apply some reinforcements to gather some level of stability that we feel comfortable with. So let's apply some reinforcements, long-term design strength of 685 pounds per foot, a length of about 20 feet. All of a sudden we have a much more informative safety map. The critical failure surface from A to B is 1.33, and we usually feel pretty good about that. Now notice there's still that big red swath, and some of it extends beyond the reinforced soil. That's implicative of a global failure mechanism, but something that can be considered. But if you look within the reinforced mass, in the area where you consider internal stability, you might notice there's orange, yellow, green, cyan, blue. Blue represents a factor safety of greater than 3, and that's pretty over-designed. We're not really gathering much on the actual reinforcement loading within the internal soil by doing this. We know we can meet a design requirement of factor safety of 1.3, but it's not very efficient. So what we'll talk about is an alternative solution that uses the same exact concepts, but flips it around. And you'll see what I mean. What that's called is the baseline solution. So the baseline solution is basically the inverse of the safety map. Now let's refresh our memory. That safety map finds a spatial distribution of safety factors, SF, for the reinforced soil. And those safety factors, depending on what reinforcement strength or length you choose, varies throughout a system. And there's probably a critical, right? A critical, the lowest factor, the factor of safety, the lowest safety factor. However, by doing this, we're only determining Tmax. Many surfaces are significantly over-designed. There's nothing about connection capacity or pull-out encountered here. The baseline solution takes that same set of surfaces, one surface, two surfaces, 10,000 surfaces, and flips it around. Now, we're not so much searching for a safety factor, considering the reinforcement strength at hand. We're searching for a safety factor of 1 everywhere. And we determine the reinforcement load at the point of intersection of every surface with every layer of reinforcement that yields a safety factor 1. And by doing this, we can kind of flip it around. It's an inverse problem. We can figure out, well, what's the tension there that gives us a limit state condition? That's what we call the baseline solution. So the factor of safety, or the safety factor in this case, it's everywhere. It's 1. And what it does is it gives us a visualization tool, in a sense, the cousin of the safety map, that we call the tension map, which gives us a distribution of tensions throughout a reinforcement, Tx, including that same value we're looking for design, Tmax, the maximum reinforcement load in each layer, as well as T0, the connection demand or connection capacity throughout, while also accounting for that failure envelope that you saw before in red and green. It accounts for pull-out at the rear end and the front end. So basically, we're getting a whole lot more information on internal stability. And it leads to an objective approach for selecting reinforcements and for selecting facing elements and accounting for connections. It achieves the same design objectives we've harped on so far, more efficient. Here's an example of a tension map here. Excuse me. So what you might see here is the same kind of color-coded map, but as opposed to looking at failure surfaces as we saw in the safety map, we're looking at the reinforcement loads required to give those failure surfaces a safety factor of 1, every one of them. So we have a color-coded scheme that represents the tension in each increment, in each piece of the reinforcement. And those are determined from those failure surfaces. Red is a large reinforcement load. Blue is small. We can see that there is a swath, or this range, this band of red that goes through the reinforced soil for the simple slope here. And that's what we'd expect. I think intuition from the safety map would give us this conclusion as well. But an interesting thing to note, you might see a black square on each layer. That represents the locus or the location of Tmax. It doesn't lie on a single surface. It might lie on several surfaces, albeit it's within a range. It might not always be. For the simple case, it works that way, but it doesn't always. You also notice that at the front of the reinforcements, that there's some load, there's some connection load that we have to meet and design. This kind of connection load might be met by the selection of facing elements, blocks or wraparound facing or mechanical connections. And we have a way of finally quantifying what that demand might be. So let's kind of go through real quick what the baseline solution is, the process of applying this in a nutshell. So the process is not so different from the safety map at the start. Basically, it's a systematic top-down process where we assume numerous, thousands of test bodies or failure surfaces emerging throughout the slope face. They can emerge just above the first layer of reinforcement at the head of the wall. They can emerge at the toe. They can emerge right through they can start right in the retained soil. All of these surfaces are exiting throughout the facing of our slope or wall. We don't care about a designation of a 20-degree batter. So for each surface, what we do is we find at the point of intersection with a given set of reinforcements, we find T required to yield a safety factor of 1.0, right? We're mobilizing the full strength of the soil. We know that if T at a given intersection with the reinforcement, well, if T exceeds the rear pullout capacity from that envelope, that green envelope you saw before, well, we can't mobilize the full strength of the reinforcement. We're limited by pullout. So the maximum load we can get at that layer, at that intersection of a slip surface and a reinforcement, well, it's whatever the pullout capacity is. It's not the full TL DTS. So what happens in that case is, okay, maybe at the upper portion of a wall, a failure surface intersects a region that's got very low anchoring resistance for a rear end pullout. Well, since we're only getting a little bit of resistance at that point, limited by the pullout envelope, that load has to go somewhere to yield a safety factor 1. So subsequently, it's shed. It's shed to the lower reinforcement layers. Again, limited in those layers by pullout if required, but basically, that load goes elsewhere, and it affects T to yield a safety factor 1 throughout. So what we do is we do this for many surfaces, like I said, thousands possibly, and we find the maximum reinforcement tension for a safety factor 1 at every piece of every reinforcement layer throughout for every surface. And we get a maximum, all these points. And the result is that every single failure surface considered is possible, and every one of them has a safety factor of 1.0. Now that's unlike a finite element where we can get a critical failure mechanism, sure, at the strength limit state, but we can't necessarily get every possible mechanism at the strength limit state. And we can do that with the baseline solution in the tension map. So again, Tx, or the reinforcement tension required for stability, is determined for every layer in the system. That's called the baseline solution, and that just means safety factors 1 everywhere. We can visualize it just like a safety map, but we can visualize it from the reinforcement perspective as a tension map. Again, you might notice this is the tension map, and that's how we visualize that baseline solution, the distribution of tensions throughout the reinforcement system. So let's quickly talk about that envelope again, that kind of busy figure with the red and green, basically the envelope for the available reinforcement tension capacity, right? Again, at the front, it's limited by pull-out at the connection or the front end. At the rear end, it's limited by pull-out starting at the rear of the reinforcement. And now recall, pull-out is basically governed by overburden and friction and anchoring length past a given failure surface. So, step 1, that's the results from the baseline solution. That red over here represents the distribution of tensions from the baseline solution for a given single reinforcement. Notice that it's remarkably planar, linear here. And the reason for that is that it is dictated, it is limited by that rear end pull end constraint, right? We talked about how if a surface passes through that, the maximum available capacity for tension is limited by rear end pullout. So that explains that linear feature there. Of course, at some point, the tension decreases, and it might go to something at the face. So we have these rear end pullout constraints, and it limits the maximum available T for a given set of many surfaces. We also talked about front end connection, but I haven't talked much about that. If we look at front end pullout resistance, really flip it around from rear end, we're looking at the front end. Again, it's resisted by overburden and friction on both sides of the reinforcement. We can see that for the given tension map, for the given baseline solution, and the tensions associated with this reinforcement layer, well, we're not good. We're not satisfying front end pullout. So what we know is that, okay, we have this frictional resistance along the reinforcement that resists front end pullout, but it's not sufficient in the front part of the reinforcement. I have to shift it up. I have to shift that envelope up to meet my conditions. And what that does is it gives me T naught right here. That basically tells me how much I have to shift up that reinforcement, or shift up that failure envelope for front end pullout. And basically what it represents is connection capacity that we require. So for front end connection, we might meet that capacity with blocks or certain facing systems or mechanical connections. But now we have a quantitative means of defining, well, what number do we need? What resistance do we need? And T naught represents that number. let's go back to our beautiful fireworks stand in Alabama. Here, we had failure, and it included the reinforced mass, not just the connections, often a sign of kind of percolating water. You can tell by the mud stains on the wall as well. So if we know that water is seeping into a system, well, that decreases the effective stress. Our effective stresses are basically what gives us resistance, right? If we have friction and the effective stress decreases, our frictional resistance decreases. So that increase in effective stress from the ponding of water, pursed water, decreases soil strength, and it basically increases the load throughout the reinforcements. What that means is that basically our envelopes for rear end and front end pullout are decreasing. So we're not necessarily mobilizing the full reinforcement strength anymore. So that weakened rear and front end pullout envelope didn't allow for us to even get that long-term design strength. It didn't allow for us to actually mobilize the full capacity of the reinforcement itself. Basically, in a nutshell, a large tension and reinforcement, it needs a large connection load to allow it to actually be mobilized. If there's insufficient pullout resistance when you go away from the face, the geogrid, it can't even mobilize its full strength. It's limited by connection. And the result is, as you see here, it's a beautiful failure. I guess beauty is in the eye of the beholders, but I mean, that's textbook. Let's talk about application in design, because that's really, you're all practitioners and you're out there doing the real stuff. So let's talk about how this might be applied in design. The baseline solution, which we discussed, safety factor 1 everywhere, getting tensions in the reinforcements, is a comprehensive assessment for both internal and compound stability. Another consideration that often is critical and can bite us if we don't do it. However, current design requires direct assessment of both internal and external stability, as well as compound and global stability. Thus, to kind of be compatible with current design, the baseline solution, it still works. Stage 1 is internal stability. That's the baseline solution, the tension maps you saw there. We get T0, we get Tmax. And stage 2 is the conventional external stability applied via the conventional reinforced slope stability analysis. So, just to reiterate, stage 1, we're talking about an alternative to internal stability. Safety factor equals the factor safety. It's 1 for every surface, everywhere. For soil strength, and we get the baseline solution. With the baseline solution, we can find the distribution of reinforcement tensions, considering the envelopes for front end and rear end pullout, and all the surfaces combined, and get Tmax as well as T0. We can get max Tmax. We can find the largest Tmax for every layer, and that's probably what we're going to go with. People sometimes choose different strength reinforcements throughout a system, but things get complicated in implementation for actually building the structure. It can be confusing. So let's just say we get a max Tmax for select geosynthetic for design. The long-term design strength in conventional design means we have that max Tmax, that maximum reinforcement load throughout the system, and we have a factor safety on strength, maybe 1.5, and we get the ultimate long-term design strength by also applying reduction factors. Those might be for creep, they might be for durability, they might be for installation damage. So this internal stability approach is completely compatible and a robust alternative to internal stability as opposed to what's at NASHTEL right now. And the nice thing is it's consistent with the principles of limit equilibrium, the principles of statics. It's not arbitrary. It fits within what your engineering intuition tells you. So, global stability. Now we did our stage 1. We got our baseline solution. We got max Tmax. We got T0 throughout. We've now kind of picked our reinforcement and facing elements also to meet that T0, that connection demand from stage 1. We have a layout that we feel pretty good about. Now, of course, we have to ensure that that global slope stability doesn't bite us. What that means is that for the given selected facing units, or the layout of reinforcements, or the reinforcement strengths determined from the baseline solution, we've got to make sure a factor safety is greater than 1.3 for all feasible failure geometries. And if it's not, we've got to change something. Might be the length of the reinforcements or the strength of the lower reinforcements, or maybe ground improvement techniques for foundation material. But we got to meet that prescribed 1.3 factor safety. So stage 2, that's standard. That's currently what people do in reinforced soil design. It deals with that global stability, including sliding at the base, a two-part wedge, or foundation failure, bearing capacity, or a global failure that just completely circumvents your perfectly designed reinforced structure. So along the critical slip surface for stage 2, all the layers are assumed to carry the equal Tmax that you determined from stage 1, limited by front and back pull-out. But stage 1 gives us so much more opportunity to be innovative for those limit state conditions for internal stability. And we examine local needs, internal stability for preventing overstressing in stage 2 by selecting the right reinforcement from stage 1 and the right reinforcement length. So stage 1 basically provides us a rational basis for picking our long-term design strength, for picking our facing elements, for considering all these kind of complexities that aren't so easy to assess using conventional approaches. Stage 2, it doesn't provide us connection loads or other internal stability diagnostics. So stage 1 is really important. So again, here's a tension map. Current application of limit equilibrium implies that Tmax, it's on one surface. And while that assumption has done us fine so far, for the most part, sometimes it's really not, and that can even be problematic. So current application of LE implies, yes, the locus of Tmax, the location of Tmax, is on a singular surface. But our baseline solution shows us that, well, not always. So we have a means of kind of offering a rational remedy for stage 2. Here's why stage 2 is important. Another beautiful failure. That's a nice wall, a very nicely designed MSE wall, made with just some fabric with some reinforcements here. And it looks like it was designed fine, with the exception that a global stability mechanism was not considered. So that beautiful wall, well, it went skiing. So let's talk a little bit about design examples, some illustrative examples to show application of this. This will be a lot more pictures and a lot less busy text. Let's start simple. Got a simple problem here. 20-foot tall wall, batter of 8 degrees, uniform spacing for 10 reinforcements, 24 inches between them, the length of 14 feet. That meets our L over H ratio of 0.7. We've got a reinforced soil with the material properties shown, retained soil, the material properties shown, a foundation soil as well. Well, let's run stage 1. Let's get the baseline solution. On the left, you see the baseline solution. It considers rear end pullout as well as front end pullout. And on the right, you can see a comparison. In blue is Tmax and T0 from AASHTO, current design, earth pressure based approach. And you know it's an earth pressure based approach because of the linear envelope that's just representative of earth pressures in the tributary areas contributing to reinforcement loading. It's linear. In red, actually, one other note on AASHTO is that in AASHTO, we assume that T0, the connection demand, is the same as Tmax. It's a conservative assumption. And that conservative is okay, but sometimes it doesn't do you justice. And sometimes it's not even conservative. In green, we see T0. That's the connection demand determined from the baseline solution. You can see that it's actually quite variable throughout. At the upper part of the reinforcements, the upper layers, we see a larger connection load. There's not a lot of resistance up there for pullout, so the connection load can be pretty big. We can see that it even can be bigger than what AASHTO tells us. This is basically remedied by the fact that many people place mechanical reinforcements in the top couple of layers of the blocks at the upper part of the wall. Now, if you look at the rest of T0, the connection demand, it varies throughout. It has a shape that maybe isn't completely intuitive. And that's not something that you can easily determine except using some kind of approach like this. Tmax, now remember safety factor is 1 everywhere, so we're trying to meet that. And since it's a pretty simple slope, Tmax ends up being moderately uniform. It tapers a little bit at the top and bottom due to connection. But what we get is that T-alt, or the T-alt determined from AASHTO, is about 4,040 pounds per foot. Using this approach, which is completely based on statics, gives us 2,124 pounds per foot, just about half. Now remember, stage 1 is great. Internal stability, we can get a real nice visualization and quantification of the demands required for efficient design of these structures. But we always got to check global. We always got to check external stability too. So here is a global stability analysis, and we see, using a safety map, well, we see that for our long-term design strength of 1,070 pounds per foot, using the reduction factors, well, our minimum factor safety is 1.31. That's greater than 1.3, so we feel pretty good about that. Note that the critical failure mechanism barely straddles the bottom reinforcement layers, and if we were to lengthen the reinforcements, most definitely the factor of safety would increase. There's been a lot of talk about close spacing in reinforcements. So let's talk about the baseline solution applied to this and quantify what we see. So we take that same wall, same material properties, but we double the number of layers of reinforcement. So now spacing is 1 foot versus 2 foot. So, okay. If you look at the left, you have the baseline solution. And on the right, we have a comparison of the 2 foot spacing that you saw in the previous example to the 1 foot case. So in red, we have 2 foot spacing. We see that T-alt for the 2 foot spacing case is 2,124 pounds. And that's factored from the max T-max, which is 700 pounds, just about. That's what you see in the red line right here. Max T-max for close spacing, well, you can see it drops pretty significantly. There's a lot of load shedding between these reinforcement layers. There's a lot of sharing the load of all of these slip surfaces with a factor safety of 1. So, understandably, the reinforcement demand, max T-max, it decreases. Perhaps what's more interesting is if you look at the connection demand, T-naught. Red dashed line represents the wide spacing case. Green dashed line squares, that represents close spacing. What you notice is that when we go from wide spacing to close spacing, connection drops significantly, at points even dropping to near 0. What that tells us is that, there's been a lot of talk about close spacing for walls, and it's often a function, what people have observed is that you need very little facing to resist the soil there for connection loading. And you can see this quantitatively here. That happens. Here's the tension map for the system. Now, it's still a pretty simple geometry. So we see a band or a swath of the maximum reinforcement loading lying within one region. However, the max T-max is not necessarily determined from a singular failure surface. Here, we're shedding loading also based on pullout at the rear end and then shifting for the connection demand. Again, we have to run our global stability analysis. We run it with the lowered required strength from those close spacing reinforcements, and we get approximately the same factor safety as before, 1.31, approximately the same mechanism too, when we look at our safety map. An interesting observation for the safety map is that we have 2 bands of instability, or kind of these unstable ranges, one internally, one externally. But notice that the internal band is not critical. And that's kind of captured by the tension map and the baseline solution. So one might ask, can we get the same benefits of close spacing, perhaps by also maybe sometimes accounting for secondary reinforcements? So that means we have our primary reinforcements, they're 14 feet long or quite long. Maybe we alternate close spacing with a short reinforcement, just 5 feet, let's say. So on the left is the baseline solution, and on the right are the values from it. So that's T-max for each layer, as well as connection loading for each layer. So in the green, let's look at T-max, green right here. That's T-max for the close spacing case. However, red is secondary reinforcement, these short reinforcements. Notice that in the secondary zone in the upper portion of the wall, it alternates wildly. The reinforcements are pretty short, so the rear end pullout kind of governs quite a bit, and a lot of failure surfaces don't actually intersect these secondary reinforcements. Thus, the loading has to be shed in a lot of cases to the longer layers, and that's what describes this kind of wiggly behavior right here. But maybe what's interesting is this. So our max Tmax goes up, sure, but look at connection loading. Red versus green. One has secondary reinforcement, one just has a single length of reinforcements, close spacing. Using secondary reinforcements, we can drop the connection loading quite a bit. So that's a big benefit right there with less reinforcement material and less construction time for that matter. Excuse me. So here, we've got to do our global analysis as always. We see that the factor of safety is less than 1.3 now. The critical slip surface actually enters the reinforced soil, exits at the toe, and we're not doing well. We have 1.21. So in this case, because we've reduced the length of the reinforcements down at the base, we're probably going to need to lengthen them. Let's talk about seismic real quick. Let's take a pseudostatic acceleration of 0.3 Gs, and let's look at the tension maps from those, from the baseline solution. On the left, that's the case, close spacing reinforcement, and the tension map that you get considering no seismicity. On the right, there's 0.3 Gs. Note the effect on the location of Tmax, that red band of the largest reinforcement loading. That band shifts wildly. Now, if you've done any seismic design for slope stability or reinforced slopes, your intuition tells you that whenever there's some kind of horizontal pseudostatic coefficient, our surface deepens, or a reinforced surface deepens. And you can see that here. Here that band exits at the toe, as you might expect, and goes directly to the midpoint of the wall where it exits into the retained soil. So in this case, we're actually capturing the reinforcement demand of a compound mechanism, of failure surfaces that pass through both retained and reinforced soil. So here we're able to capture the demand, not just for internal stability, but compound. And that's really quite important, because in a compound failure, you might not be mobilizing the reinforcement strengths of the upper layers of reinforcements for the critical failure surfaces. There's the baseline solution, that is just tensions in each reinforcement here, and you can see on the left that, again, there's a band that essentially follows all the way to the midpoint of the wall, representative of a compound mechanism. So, in green, let's look at Tmax. This was Tmax for close spacing reinforcements, no seismicity. In red is Tmax, considering 0.3 Gs. At the top of the wall, it increases a little bit, and that's because a lot of the failure masses up at the upper portion of the wall, well, since they don't weigh a lot, the mass isn't big, the inertial loading from a PGA is also not big. It's a function of weight. But as we go deeper and the failure masses get bigger, we see that, okay, Tmax increases until it hits this point. And you can see that we capture that point where that compound failure mechanism that really governs here enters the reinforced soil zone and increases the demand of reinforcements. This isn't easy to predict with conventional methods. If you look at connection loading, well, we see something similar. There's a little bit of numerical inaccuracy here, but we see that connection loads particularly increase in the lower part of the wall. Again, global stability analysis, and just as your intuition has confirmed, well, our surface deepened. For the given design loads that we chose for the long-term design strength for seismic, well, we can ignore the creep reduction factor because it's an extreme condition that's transient. Well, our global slope stability analysis is 1.04. And under seismic loading, that can be okay. It depends on your local code, but considering that it's an extreme event, that might be all right. We'll get through this and just go through a couple of quick examples. Let's talk about that arbitrary threshold of a 20-degree batter. Let's compare the first case, 8 degrees, 10 layers, with the same slope, same conditions, except it has a 26-degree batter now. What we see is that red, 8-degree batter, green is 26 degrees. We see that Tmax drops significantly, as well as the connection load throughout the system, you can see here. So there's advantages sometimes if you have the space to build a slope instead of a wall. But we don't have to draw an arbitrary distinction between a 20-degree batter or anything like that for what we call wall or slope. They're all the same thing. Physics works just the same. Okay, here's a simple 2-to-1 slope or rotational failure. Here's our global stability. We see that the critical factor of safety kind of passes through the lower reinforcement. So to attain a factor of safety of 1.3, we had to add longer reinforcements at the base. All right, let's talk about the walls that we really kind of deal with way more commonly than code would say. So here's a complex wall. I think we all agree this is pretty complex. We got sandstone as the retained soil. We have select backfill for the bottom part. We have local backfill for the upper part. We have tiered geometry, a wall supporting a slope with a broken back. And we have a live load of 250 PSF, all on that. I think most people would agree that's pretty complicated. But these are systems that people are designing and they have questions about. Here's your baseline solution. We can see, especially at the top, you can see what's dictated by pullout. You can also see the reinforcement distributions throughout, and they're pretty wild. There's local maximums and other maximums, and this isn't easy to predict using the conventional approaches we do today. There's the tension map. Note that we do have a red band, that swath of maximum tensions. But however, it's not the locus, or the maximum point doesn't lie on one surface, and in fact, it contracts and expands based on backfill geometry. There's also other local maximums occurring here. There's no other way to capture this kind of mechanism and this kind of visualization of reinforcement demands. Here, just visualizing the actual connection and Tmax, we see that connection loading at the head is very high. The reason being because we have that local surcharge. So using this approach, we can account for surcharges, whether it's a live load from traffic or a crane, whether it's a dead load from a bridge footing. Whatever it is, we can account for that using statics. And you can see that it wildly varies. It's not so easy to use intuition to predict what this might be. You can see Tmax as well. Again, global stability analysis. Critical factor safety is 1.36. We feel good about it. So, some quick concluding remarks. We have a little bit of time for questions. Limit equilibrium solutions may capture the limit state conditions for reinforced soil structures. That's been shown before. However, the current way we apply it, it can't give us all the information that is frankly useful. It can't give us distributions of reinforcement tensions and demands in each layer. And with the baseline solution, we can do that. The baseline solution provides us a means of finding that maximum reinforcement load that we're always looking for. And it might not lie on a single surface. We can also get the connection demands, and we can directly account for pull-out resistance and satisfy equilibrium. It can account for complex geometries, unique reinforcement layouts. It gives us a quantitative background about how to select facing units, and what demands and resistances these might have. Water, more, whatever you want, surcharges. The baseline solution can be visualized through a diagnostic tool called a tension map. Like its cousin, the safety map, it's a color-coded approach to present mobilized tension demands in a system. The presented approach, the baseline solution, provides a rational means of designing these reinforced soil structures. Simple, complex, but still remaining compatible with the current way we do things. It uses the same exact physics that you know, but it applies them just a little bit differently. And by doing that, it gives us a whole lot more information that we can use to do better design or more innovative designs. So with that said, I will have some time for questions, but if you need any more information, I can give you some easy bedtime reading here. We have Report Federal Highway Administration from the Federal Highway Administration right here, Limit Equilibrium Design Framework for MSE Structures with Extensible Reinforcement. We have a recent paper in Geotextiles and Geomembranes describing the process and kind of the quantitative nuts and bolts if you're interested. We also have software that actually applies this. It's called RESA Plus. It was just released. You can find it at geoprograms.com, or you can email me for more questions if you're interested. But at this stage, I'm going to hand over the mic to John. John, please take it from here.
Well, thanks, Ben. That was a great presentation, and we've had a number of questions come in. I'm going to start with an easy one that I'm going to lob to you.
Okay.
The first question is what software package is being used to generate the tensile forces? And I'm going And I want to piggyback a question. My question on that is, in all of your cross sections that you showed, were you setting the phreatic surface at the very top of the wall just for conservatism?
Oh, okay, great. All right. So for the first question, the software is called RISA Plus. You can go to geoprograms.com or email me for more information. My contact information is there. But all of these distributions were used with this program right here specifically. And happy to provide any more information. It's just a select few examples we showed. And John, to your question about the phreatic surface, in the cases for all these little simple examples I showed, we actually didn't account for water. But you could directly account for water, and that would, since we're doing a slope stability analysis, that would be accounted for as a pore pressure affecting the effective stress or effective strength of each surface analyzed at the intersection beneath the phreatic surface. So you can account for water in the reinforced soil or even ponding water outside of it. But in these simple examples, I ignored water, which is a big thing to ignore for sure.
All right. Long as we're on modeling questions, let's take the case of a external corner. Do we get into 3D strain considerations?
Yeah, the corner problem is a tough one. Actually, so as you notice, these are all plane strain conditions or two-dimensional conditions, and that's kind of conventionally what we do in design. When you start to get into design for corners, it's really kind of gray. It can be gray. And when we talk about corners, actually, since it's a 3D case, often you would expect that, frankly, the reinforcement demands would be lower. We can't incorporate that in this approach, but because it's 2D. But in a 3D approach, since we have this kind of three-dimensional geometry and these boundary forces acting on a three-dimensional failure surface, that actually there's more resistance in the soil, so the reinforcement loads will decrease. However, an interesting paper just came out this past year that does show that, but since the mechanism changes, so does basically it deepens. So while reinforcement loads might decrease, great, at a corner, the surface might deepen. So pull-out might actually be more critical. So often at the corner, one thing you got to consider is the depth of failure. So unfortunately, this software package doesn't account for corners, but most conventional design is done in 2D because 3D it's a can of worms.
Okay. Now, you spent a lot of time talking about pull-out connection strengths. Mm-hmm. One of the questions that came in was with regard to how a contractor compacts the backfill behind the wall facing, and how do you account for settlement of the material and basically getting a step down off where the reinforcement material comes off the facing and into the earth mass when that settles and you get a step down effect coming off the back of the facing.
Right. So down drag essentially and kind of localized settlement and parasitic loading at the connection from, yeah. So that's a great question. And actually it's one of the limitations of a limit equilibrium approach is that we're really talking about the strength limit state, and that problem is more of a service limit state condition. Whenever there's, say, compaction in the backfill, especially near the facing, there's some residual loading left over in a reinforcement. Whenever there's kind of uneven settlement, particularly between kind of that stiff column of blocks or facing unit and the reinforced soil, you might have this kind of parasitic load that appears at the facing. So indeed, there might be some loads that are higher than you might design for, considering these serviceability conditions. However, we're often applying a series of safety factors and reduction factors to kind of make sure we feel a little bit comfortable with the level of loading that we might see there. So it comes down to a construction issue, it comes down to a serviceability issue, and as I mentioned at the beginning, often we hope, and it's been shown generally, we hope that sufficient strength limit state design will provide us at least some confidence that we'll probably meet serviceability criteria as well, which we're much worse at actually capturing without complex numerical models.
When I've seen this problem addressed, it becomes a construction quality assurance issue, and having a qualified person on site to monitor construction, which I know is challenging in some wall design budgets.
That's exactly right, John. Exactly right. It's usually very difficult to compact up there near the face, and that can result in some problems down the road.
Okay. Next question. One of the viewers believes that the assumptions to model the lower the connection strength at the lower part of the wall, is it based purely on computer modeling, or are there instrumented walls or structures that correlate the modeling?
Right. So this has been compared to a series. So this has been compared to some numerical models. It's also been compared to a series of centrifuge experiments and monitored loads. The thing to be very clear about is that this is a tool meant for strength limit state conditions. So that means we're talking about imminent failure. We have to design to make sure the structure doesn't collapse or slide away. And when it comes to most of our structures, very few people are willing to volunteer their structure to fail. So in terms of monitored data for the strength limit state, there's not a whole lot, right? So what we're left with is experimental data. So centrifuge testing, high quality centrifuge testing from actually UT Austin and elsewhere. We get results that match quite well with numerical modeling compared to, say, FLAC. We get results that match quite well for the limit state conditions. And so some of those examples are in the reference manual that I show up here. But again, this is for a strength limit state.
Okay. Questions are coming in faster than I can link them together in a cohesive manner. But going back to our corner radius, is there a radius to height ratio where the corner problem transitions, like a 2D to a 3D problem? Are there some rules of thumb to work by?
Oh, that's a great question, actually, very practical too. I don't have a specific answer or rule of thumb there, and as being an academic, my answer is always it depends, right? Yeah, I don't have an answer to that, but I'd be happy to at least send some references that describe the corner problem. Basically, as you start to approach, if you have a corner angle, 90 degrees being a right angle for a corner and 180 being a continuous plane strain wall, you will start to see basically degeneration into plane strain conditions as you approach 180 degrees. But the problem is that it's still rather 3D up until that point. And even under just a wall length, not considering a reinforcement, not considering, even under a given wall length, even not considering corner, that is, you still might you have a finite length of wall, and you still might have 3D conditions. So I know that at least for 3D conditions, for reinforced walls, we typically see a degeneration to approximately plane strain conditions around a height to width ratio of 10. But, you know, infinity theoretically is when it happens. So for a corner, no, I don't have an answer, but it's a fantastic question, and I can at least point this individual to some references. It's a great question.
Okay, we're going to get two more questions in here, and what I see happening is I see the need for another webinar on more detailed subjects and more specifics going forward. And so I'm going to ask you back.
Sure, happy to.
Okay, so
anytime.
Here, I got to thank you from this individual. I could not understand how these values of the tension map will be used. Can you just go back and touch on that briefly, and
happy to
give an example of finding this map on one of the strips and how you would select the strip?
Right. So let me take a simple case. That's the best case. So what we do here, and just to reiterate, is that we look at lots of potential failure surfaces the same way you do a reinforced slope stability analysis. But as opposed to finding just a factor of safety of whatever it might be for a given reinforcement strength and doing a trial and error process of changing your reinforcement strength till everything meets a factor of safety of 1.3, well, what we do is we determine, given the full soil strength being used, like an active wedge, if you will, instead for thousands of surfaces, well, what reinforcement load is required to maintain that limit state. So what that does, it gives us that baseline solution, and that's just a name for basically a distribution of tensions for each layer of reinforcement. Now, this is one way to visualize it. The tension map just happens to be another way to visualize that for each reinforcement. And the way it's used is that we can use it to determine Tmax, just as we've conventionally done through trial and error, but we can do it in one step. We can also use it to determine the connection demand. So often we assume, say for AASHTO, that Tmax is the same as the connection demand. And, you know, as maybe relating to that previous question, that could relate to being conservative regarding down drag and parasitic loading and all those serviceability issues, right? But we can also get a T0 value derived from this approach and basically use that to, say, select a mechanical connection that has sufficient strength to meet that connection demand. Choose a block that meets that connection demand. And you can account for blocks in this approach. So those are the two big pieces of information. But maybe that's underselling what's also implied or implicit here in the fact that we're also directly accounting for pullout at the rear end in this one stage. So basically it's doing your multiple little modules or components for internal stability in one and giving you both connection demand at the face and that Tmax, which might not always be the same Tmax that you get from your trial and error process.
Oh, okay, thanks, Ben. All right, I don't think we're going to be able to get up to all the questions that are continuing to come in. So we're gonna finish with one last question. This is your loaded question, knowing who's attending this webinar and going through the attendees list. Do you think AASHTO will adopt this methodology and or NCMA? And can you talk to the conservatism level between the methodology you've presented versus other methods that are out there?
Oh yeah, that is a loaded question, but it's a good one. It's a really good one. So with regards to AASHTO and NCMA, there is some talk about many different methods possibly being adopted. This being one of them. Nothing is guaranteed. We don't know. But essentially, it's still just it's compatible with the current way that we assess compound stability and reinforced slope stability. So it's not really such a big jump, to be honest with you. With NCMA, I can't really speak to that. And with regards to the level of conservatism shown, it's always really hard to say how conservative or how not conservative. We have, as I said before, a comparison to experimental tests in a centrifuge, which models larger scale conditions. We have comparison to numerical models, but the fact is, a lot of the failed MSE structures we've seen, well, nobody's intentionally designing to fail in a strength limit state. Often they fail due to poor construction or other conditions that kind of dictate why they fail, water, for example. But we don't really have that much information on them. So unfortunately, it's tough to say whether there is whether something's very conservative or not. I think we all feel pretty confident that the current AASHTO approach is pretty conservative, but in some cases it might not even be adequate, especially for connection loading. We're losing some information for a designer to make an informed design. So this approach is based on statics, on physics. People hopefully trust their slope stability analysis when they run slope W or rock science or whatever it might be. They trust their analysis. This is based on the same physics of this approach, and it's based on a strength limit state, which is often the most conservative limit state that we have. So in terms of conservatism, all I can say is that this is based on the physics that we used for all different types of designs in geotechnical engineering. And it's compatible with what we currently do for compound and global stability. So conservatism That's a very much it depends answer. But compatible with what we do now, yes it is. And we get more information that we can use to choose a safety factor or a margin of safety that you as an engineer would feel comfortable stamping on a plan.
Thank you, Ben. If you can forward to the end of the slide deck, we'll wrap things up. I'd like everybody to, if you could stick around for just 2 more minutes, we'll get through some upcoming events. And so first I want to say thank you, Ben, for taking the time to put this lecture together and visiting with us.
My pleasure, and thank you all for being here. I really appreciate your time. And please feel free to send me questions. I'd be happy to answer them.
Okay. So before we wrap up, I'd like to mention some ways that everyone could become more involved with IGS and GMA. First is membership. Members are really important to both organizations. Without becoming members, we don't have the ability to put on events like this and continue to deliver free curriculum to all of you. So if you like what you heard today, please go into either the IGS North American website or the GMA website and sign up to become a member today. And that gives us the ability to continue to deliver more content. I know IGS has several more talks lined up from industry experts. The next one coming up is going to be on December 4th, where Professor Hahn is going to talk to us about reinforced road design. So we're gonna go right from Ben's subject matter and reinforced walls. We're going to go into reinforced road. And then we'll talk to both of these gentlemen about continuing to expand on the knowledge base that we've delivered here today. So twice a year, GMA also goes out and lobbies state and local governments and federal government. The next DC lobbying visit, where we're going to talk to the federal government, is coming up on November 13th and 14th. If you're interested in participating, please reach out to Jonathan Curry and his team at GMA. And then lastly, you have a chance to interact with us live and in person at our open meetings that are going to be at Geosynthetics 2019 in Houston, and where we'll have everyone's annual meeting at the big Geosynthetics conference. And then lastly, we've got IGS has a Educate the Educator plan in San Diego at UCSD. So if there are any professors on the phone who would like to get some training in geosynthetic curriculum, please look in the coming months for the sign up for that. With that, we will conclude today's meeting. Once again, thank you, Ben, for putting on this presentation, and thank all of you for attending.
Thanks.